Hello, Dr. Chad McGee again here. Let's talk some more quantum physics. You know, you just can't resist. Okay, so the thing is, today's lesson, what I want to teach you, goes into the solar part of it. Okay, we've talked all about what's the inner workings of inside of atoms, what makes up particles and stuff. Let's think bigger. Okay, now I do want to review a little bit briefly, and that is looking at my model of what a neutron looks like. Remember, it's got 3 spin paired sets of light momentum vectors, but that means that there's no net light momentum vector overall. Okay, so that leads to some instability. Protons do have a net momentum vector. Okay, they have 2 pairs and then 1 that's not paired. That means that light does have a net momentum. It's going to be happy. And so that's why, of course, protons tend to not decay very readily. Now, let's talk about stars. I know people like to talk about astronomy and they love talking about what happened when stars get big and they start dying. What's going on? Well, when you have a star and it's big and it's compressed and it's going through its nuclear reactions, it can get to a point where it has so much energy where it basically collapses amongst each other. Okay, basically the masses get so big and it crushes itself and it ends up forming a neutron star. Okay? So what this means is if you have a big enough mass, the process by which it does is that it basically crushes the inner workings of it to the point where all the atoms inside become converted back to neutrons. So in other words, it's a form of E equals mc squared. Okay? In this particular case, the light is escaping. We're still seeing the star, but it gets to a point where it basically doesn't give off the light. And it comes to the point where it basically crushes amongst each other. And then protons and electrons and neutrinos and antineutrinos and all that combine, and your net effect is you're just going to have neutrons. Now, I do want to talk about larger stars. Larger stars will also do E equals mc squared towards the end of their life, except they end up forming something we know as a black hole. Okay? And that is to the point where the gravity field became so great that not only did it form and process and crush everything, but it formed and processed and crushed everything around it. In which you eventually form an event horizon to which nothing can escape. So essentially, as things fall in, they're gone. Okay, well, not quite. This is something I want to bring up, that there is a relationship between neutron stars and black holes. Okay, this is my representation of what I think goes on inside of one of these guys. Okay, now I have kind of a strange way of, oops, no, I messed up already. Ooh, sorry, not the best draw in the world, apologize. This is my representation of thinking about what's a black hole. Okay, so you kind of have this obelisk disk thing. You can think of this as your event horizon. If things fall into here, well, they undergo a process. Now, this is how I like to represent it. Here's your center of mass. Okay, center of gravity force. Okay? So in a black hole, everything that falls in is eventually going to fall towards that center of gravity. Okay, it's not center of mass, is it? Well, actually, we'll get to that in a second, but it falls towards the center of gravity force. Okay? So net effect is if things fall in, they go down that way. Well, the thing is, the forces become greater and greater as you get closer and closer to that center of gravity force. In other words, there is a line somewhere in here where the gravity force is very strong enough that it does something weird. In other words, we go back to the Einstein's equals mc squared equation, except now we have done a transformation. Matter and antimatter are converted back to electromagnetic energy. So electromagnetic radiation, i.e. light energy. Okay? So what happens, I'm going to represent this guy. Let's put an electron. Okay, forming an electron falls in. As this thing falls in, okay, it's going to get stretched. So one side of this molecule is closer towards that center of gravity force. The other side is a little bit less, okay? Once it reaches this point, okay, what happens is this has a very great pull, and so it's going to break part of it. And now, instead of our nice, what we were usually thinking of particle, we actually have, so remember this is our cylinder part, it's basically forming our light wave. So what we have done is this is now light energy that travels to this source, okay? Now light wave by itself, if you have a light wave, of course it's going to continue being a light wave. Now, the catch is what happens when it hits here, okay? Once it hits there, this is when light bends upon itself, okay? And it turns out, if it's going to do that, it's going to form the simplest mother of matter, and that is neutrons are born. So the net effect is, what I want to tell people is when you have a black hole present somewhere out in that universe, it is tied with the neutron star. The beginning point of the black hole ends up with the end point of the neutron star. Now there's a catch to it though. This neutron star does not necessarily have to be in our dimensionality. This guy could be possibly lower dimensionality, at our dimensionality, or higher than our dimensionality. And that means that other dimensionalities are now tied with us, because they potentially may have black holes that link with our dimensionality, okay? Because that's where their neutron stars may dump their energy at, okay? So correspondingly, this is the thing where I talk about dark energy and dark matter. They might actually be matter and energy forms that are just higher dimensionality. If they're of a different dimensionality than what we see, we may not be able to accurately measure them. They do exist. They are still in our universe. It's just that we can't interact with them in the same normal means that we're used to, okay? So that's what I wanted to say, is potentially that leads to us to where this stuff may come from, okay? Now that's all theoretical. We don't know. Well, it'll take many years to figure out. Hopefully in our lifetime, we'll see that, okay? But I do want to point out that correspondingly, based off of what I understand with the particle, as things flow through here, your light wave will eventually get over to here, bend, and become matter again. So at this point, we are undergoing another E equals mc squared, except this time we're going back to matter. Okay? So Einstein's special theory of relativity is extraordinarily useful in the universe. That transformation is what allows us to get to this. Okay? In the particular case of this guy, the neutron star, we're typically going just one direction. In the case of this one, black holes are actually going in two directions. It turns out we're doing one direction to relate to light energy first, and then going backwards to make the matter. Okay? Correspondingly, yes, out in the universe there exists the potential where you could have black holes swirl the other way and potentially could lead you to an anti-neutron star. That would be very interesting to study. Okay? Correspondingly, what would be the anti-neutron? Well, it's exactly opposite to this directionalities. Okay, you know that. You've seen my videos. Okay, so this is what I wanted to talk about when it comes to how do the small parts of quantum mechanics play in with the great big parts of the universe. All right, so hopefully it gives you something to think about, and we'll talk next time.